So our speaker tonight is Dr. Jorge Moreno. He's an associate professor of physics and astronomy at Pomona College. He was the fourth ever Mexican scholar to receive tenure in astronomy in the U.S. It's a wonderful thing, but also think about fourth ever and how young we are. In 2023, he was the recipient of the Vera Rubin Distinguished Professorship from UCSC. Dr. Moreno has worked at the intersection of astronomy, pedagogy, mentoring, and art, so focusing on helping us advance the ways we teach and mentor astronomy nationwide. Scientifically, his work focuses on using large supercomputers to better understand galaxies, and all the things that they do, how they form, evolve, exist. His work on galaxies without dark matter is particularly exciting, because if you ask the normal astronomer, they would tell you that's not possible. And so it's really fun when someone starts pushing the boundaries of what we think can exist in the universe. So please join me in welcoming Dr. Moreno.
Thank you for the wonderful introduction. I should also say that you were my student. And in addition to being a professor and an astronomer, I'm also an artist, I'm also a mentor, I'm also a teacher. I'm also a prankster. I like to cause trouble. So I'm going to trick you during this talk, and also I'm going to give you a quiz. So you better pay attention, okay? Well, galaxies lacking dark matter. What are there? Where are there? How many are there? How does nature even make them? For the better part of the last 15 years, I've been obsessed with galaxies and dark matter. And the reason I love galaxies is because they're a lot like us. They're a lot like people. If you pay attention to my accent, my mannerisms, the clothes I'm wearing, the things I like to eat, you can infer something about my family, my communities, my ancestry, my culture. And speaking of culture, I'd like to start by acknowledging that we're on an indigenous land. And one way to honor the land is to think about the energy we bring in this space and how we treat each other. And also, I want you to think about who are you bringing into this space. I want you to think about your ancestors. I want you to go 3 generations in the past, maybe a great-grandparent. This can be a biological ancestor. It can be a mentor. It could be a non-human ancestor too. And I also want you to think about the future, about your children, grandchildren, great-grandchildren, which may or may not be biological or may not be human. Because everything you do is not just going to affect you and the people around you at that moment. It's going to affect 7 generations. So we have to carry ourselves with responsibility and with love. Okay? So this is an all-sky picture of the Milky Way galaxy. This galaxy contains everybody you have ever known, everybody you've ever talked to, everybody who you've loved, and even the people you've hated, they're all in here. And all of our ancestors are here. And your ancestors, no matter where you come from, no matter where your ancestry comes from, everyone has an ancestor who was an astronomer. And in every culture, people have been fascinated with the Milky Way galaxy. This is an image from how the Inca in South America saw our Milky Way galaxy. And they built a whole cosmology about that. And their understanding of the world and the universe was guided by what they saw in the sky. If you go to Australia, the Australian Aboriginals, they also looked at the galaxy, and they thought, well, this is an emu that is transversing the sky. And you might think these ideas are silly, but we don't know. Like, my computer simulations seem fancy in the 21st century, but maybe in the 31st century, people are going to be like, hey, maybe that doesn't make much sense. That is okay, because it's not so much about getting the right answer, but enjoying the process of discovery. If we go to, for example, West Africa in Ghana, the idea they had about the galaxy is there was a teenager, a girl, who really wanted to grow up, but her parents didn't let her, so she kind of threw a fit. I have teenagers, so I know a lot about this. And they had a fire, and she made this fire go up into the sky, creating the Milky Way galaxy. This is from Egypt. This is a god Ra, who protects the Egyptians, who protects all of humanity by being on the sky. And in China, they see the Milky Way galaxy, our galaxy, as a river, and the foam is the light from the stars. Now, this is Al-Sufid from modern day, from what we call Iran today. He's the father of extragalactic is astronomy that's beyond our galaxy. So Al-Sufid was the first person to observe Andromeda, our dear neighbor, and also the clouds, which are two small galaxies that are orbiting the Milky Way galaxy. And just like my wife and I came together, and we've been dancing with each other and loving each other for years, these two clouds, which are two small galaxies, they came together, they were dancing with each other, and now they join this beautiful party we call the Milky Way. And we've come a long way from what our ancestors did up until today. Now we have big telescopes in space, we have big telescopes on the ground, like the one you saw down the hall, that are able to map everything that is in the Milky Way. And now we're able to make a full sky image of our home, the Milky Way. But I told you I'm a troublemaker. What if I told you that this is the Milky Way? But this is a simulated galaxy. This is a galaxy I created in a supercomputer. Because what I like to do for fun is create virtual universe in supercomputers. And because we know a lot of physics, we're able to recreate things that look a lot like galaxies to the point that I can trick people like you. And that's why I love being a scientist. Right? So the nice thing about computers is you don't have to wait and the formation of this galaxy unfolds. All you do is you put the laws of physics, you run it, and you get something like this. What would take billions of years to observe can take just a few seconds on the screen, and we can learn a lot about this. I hope you know, well, you have the Milky Way galaxy. This is a simulated galaxy, and there was this little guy who came disrupted. It's like, imagine this room wasn't as friendly as it is. Let's imagine you're really mean. I come in the room and you kind of disrupt me completely because I'm so stressed out. This is what happened to this galaxy. So galactic lives are really dynamic. And the way a galaxy looks is like, I have an accent, the way a galaxy looks and behaves tells you something about its ancestry and its history. All right? So, but how do we know? So this talk is about galaxies without dark matter. And it's kind of like I told you, I'm going to talk about rabbits that can't speak English. And like, you're like, wait, but Daddy, you know, they could speak English, and now you're telling me they can't. So it's kind of confusing, right? Like, let's take a step back. The reality is, for the last 50 years, it's been established that dark matter is in almost every galaxy. And before my paper, all astronomers would say, it has dark matter. So this is why this idea is challenging. And I'll tell you a little bit more of how we observe dark matter and more or less what it is. We don't really know exactly what it is, but we know what it's not. And that's how physicists think. We have ideas and we kind of try to rule them out. And it's kind of like you cannot observe dark matter directly because it doesn't emit light, but you can observe it indirectly by how it affects stars that are actually things that we can see. Kind of like the ghost in my house. I cannot see my ghost directly, but I see that he folded the clothes or washed the dishes, and so that indirect evidence tells you that there is a ghost. By looking at how galaxies form and how they move, tells you that there has to be matter. Okay? So what we do is the following. We need to look at the motions of galaxies. To measure the motions of things in a galaxy, we need to think a little bit about something I call the Doppler effect. This car, and it's just sitting there. The observer and that observer are going to hear the same thing. But if I move, if this police car is moving this way, this person is going to hear a higher pitch, this one is going to hear a lower pitch. If I was moving very quickly, like close to the speed of light, and I was moving towards you, the pitch of my voice will go up. But if I'm moving away from you, the pitch of my voice will go down. The same is true if I shine a laser at you and I move very quickly. Let's say it's a green laser. If I move towards you, it's going to get bluer. And if you move away from you, it's going to get redder. If you are ever caught by cops and they give you a speeding ticket because you cross a red light, you can say, no, like all this physics is happening. Get them confused, and that's how I get out of paying tickets. Because I'm pranking. So you can use this method, and Vera Rubin was the first person to use this method, but not with sound, but with actual light. And she actually was a frequent visitor of the Lick Observatory. She would spend a lot of time here measuring how things move around galaxies. So the picture I showed you before, you can think of it not just as a painting, but as a movie or a GIF, right? Now, in reality, you wouldn't see it moving this quickly because you will have to wait billions of years to see the rotation of the galaxy. But you can know its instantaneous velocity by using this effect. You want to ask yourself, is one side of the galaxy, is it shifted to the red and is the other one shifted to the blue? And that's what people with big telescopes do. You can measure that this side is bluer and this side is redder. Well, so you can, then I can ask the question, which way is it spinning? Well, this side is moving towards you, this one is moving away from you. And when you measure these velocities are not the same everywhere, but actually changes as a function of distance from the axis of rotation. If I am a star around a galaxy, that star velocity is going to depend on two things. It's going to depend on how far away it's from the center, and also it's going to depend on the mass enclosed within that volume. So the more mass there is here, this star is going to move faster, right? I like to think of, for example, when I do laundry, and I look at clothes inside my washing machine, how quickly they are going, it depends on how far away they are from the center of the washing machine, but also the washing machine's ability to contain them, because if the washing machine disappears, the clothes would just fly away. These things are moving, and something has to contain it there, and that is the mass of the galaxy. So if we go back to our physics lecture, I told you that this velocity around the galaxy depends on how far away you are from the center and how much mass you have. So in the inner regions, the mass is winning. As you're moving away from the distance dominates, so the farther away you are, the slower you are. From physics, you go like this. But nature is also a prankster. This is what Newton's physics tells us based on the stars we observe. But this is what nature gives us. It tells us that stars are moving way faster than they're supposed to. The mass in stars is not enough to explain why these stars are moving so quickly. And therefore, we infer like there has to be something else. And this something else, we call it dark matter. We don't know what it is. We think it's a lot of tiny, tiny particles that don't emit light. People have been thinking about different possibilities, and then observations kind of rule them out one by one. We don't know what it is yet, but we know what it's not. So I just want to establish that if you ask any astronomers, we've known for the last 50 years that to explain observations, we have to invoke the existence of this substance we call dark matter. And we're really good at simulating dark matter. So if I take a supercomputer, I can put a lot of virtual dark matter particles. They evolve, they interact with each other gravitationally, and then you can start making what we call dark matter halos, which are clumps of dark matter. So you start at the beginning of the universe is really calm and smooth, and then there are regions that are slightly more dense than the average, and those are the ones that grab everything. It's kind of like capitalism. You're rich, you get richer, right? Unless you trick cops into not paying tickets. So here, I'm making a dark matter halo. This is where the galaxy is. Now, dark matter doesn't really glow. It doesn't emit light. You cannot see it with your eyes. What I'm doing in the computer is I'm putting fake colors indicating where the mass is. But in reality, you wouldn't be able to see this. So this is a representation. Like when you look at infrared, if you wear infrared glasses, that doesn't infrared, but the glasses take the infrared light and translate it into light that your eyes can see. That's what I'm doing. Light, but in my computer I can assign for each tiny halo, I can assign a color that. Okay? So hopefully I have convinced in the universe, and most astronomers believe that there is tons of it and it dominates galaxy evolution. And there is another piece of information I want you to remember, which is why when I discovered these galaxies without dark matter, I pissed off a lot of people. And the reason is this. If you look at a galaxy like the Milky Way, you can look at smaller and smaller galaxies. So this M star is the mass in stars. So you can start with massive galaxies, and then you can go into low mass galaxies. The dark component, what happens is that the fraction of mass in dark matter becomes more prominent when you go to low mass galaxies. Massive galaxies have some healthy amount of dark matter. Tiny galaxies have tons and tons of it. And the reason is as follows. So when you make stars, stars live their life, they explode into supernovae, and they like to make a mess, they like to expel gas. So if I ask you, imagine you have a cup of Americano and a cup of espresso, and you put them in the microwave for 5 minutes, which one is going to make up the biggest mess? The tiny cup or the big one? The tiny one, right? So here, because of supernova explosions, the tiny galaxies, the moment that the stars go supernova, they just evacuate the galaxy and they create a mess. And only the ones that have a really chunky halo are the ones that survive. And that's why we expect that not only galaxies have dark matter, but tiny galaxies have lots and lots and lots of dark matter. So I want you to engrave that in your brains. I want you to remember that. And now I'm going to take you into a journey. This is a tour to a galaxy group called NGC 1052. This is 60 million light years away. That might sound like really far away, but for extragalactic astronomers like me, this is our neighborhood. It's like Santa Cruz or San Jose. This is a nearby universe. And I'm zooming into this galaxy that I'm going to call NGC 1052 DF2. So astronomers, we complicate ourselves with really long names. Okay? This is a really cute galaxy. It's really what you can do with these galaxies, you can measure the light coming from stars, and that allows you to know how much mass you have in stars. It's like, for example, imagine we're all speaking and I listen to you, and just by listening to your voices, I can infer how many of you are in this room. So by measuring stellar light, we're kind of like hearing how much stellar mass. It has about 1 billion solar masses, which is, but compared to Milky Way, this is tiny. So for most astronomers, we'll call this a low. This is very much. Now, that's a direct way of measuring the stellar mass. But if you look at these dots here, some of them are background galaxies like this one, but some of these are what we call globular. Globular clusters are really dense collections of stars that live inside galaxies. And if you measure how quickly those globular clusters are moving, you can measure the total mass of the galaxy. And for galaxies like this one, if you were to compare the stellar mass that you get from the light with what you get from the motions, this is tiny compared to the total mass, because low mass galaxies are supposed to have a lot of dark matter. That's expectation. That's what most observations have told us about most galaxies, but this one is a prankster. So you can measure the velocities of these globular clusters. People use telescopes like the Lick Observatory to do that. And what they find is that the total mass of this galaxy is the same, approximately the same as the one in stars, meaning that there is no room for dark matter. Maybe there is a little bit of dark matter, but it's really negligible. And that broke all paradigms. People panicked, people freaked out. Some people said, like, well, maybe the dark matter model is wrong and we should get rid of it. Observers, they started fighting with each other. Maybe your measurements are wrong. Maybe you didn't measure the velocities wrong. Maybe you didn't measure this, maybe you did this wrong. I have been invited to talk in other continents, so others can fight with me about this, which I enjoy. I thrive in these functions. I'm okay with that. I'm cool with that. But where was I? This created a lot of chaos. And then people who do simulations like me, every group in the world, they try to recreate these galaxies, and no one was able to do this until I came along. So, and actually, after this one, there was a second one that was discovered, and these two are actually named. I'm going to call them DF2 and DF4, and they live in this galaxy group that I told you about before, NGC 10. Massive galaxy, you have a bunch of intermediate mass galaxies, and then you have this guy here, and this guy here. What I think and what my simulations tell me is that the reason they don't have dark matter is because they're strongly interacting with this massive guy. So they come, they kind of have they spar with this big guy, they fight a little bit, and then they lose their dark matter, right? That's what I think, okay? So, but actually this idea people were thinking about galaxies without dark matter even before the discovery of those two galaxies. And this is a paper from 1998. And the idea here, they say, well, we think there should be galaxies without dark matter, and the way you make them is with something called a quasar. You might be wondering, Jorge, what's a quasar? So it turns out that every galaxy has a supermassive black hole in the center. And supermassive black holes, they don't emit light, but when they get hungry, when stuff starts falling into the black hole, that stuff starts to glow. It starts to emit a lot of energy, and that energy can really push things outwards. Quasars can be even 100 or 1,000 times more massive than the entire galaxy when they're active. So Prija and friends, they thought, well, if a galaxy has a quasar, then that quasar can push gas, and then that gas can be compressed outside and create galaxies. Kind of like imagine you're making pasta and you're boiling water, so the water is boiling, and you have this steam coming up. It's basically the heat from the stove pushes the steam up to the ceiling, and in the ceiling, the steam collapses into water droplets. So this is what's happening. The quasar is pushing the gas into the outer halo, and once it gets there, it cools down and it collapses into stars, and you make galaxies. So this is the idea that these people had. And I was like, well, maybe we can test that. Back in 1998, they didn't have the kind of computers we have today, so maybe we can do better. And so we did this. So this is a simulation my collaborators and I created, focusing on a massive galaxy with a supermassive black hole and a quasar. And every frame, you're basically zooming in. And you notice that the first frame doesn't kind of move, but all of them are moving at the same time. But it's when you get closer to the black hole that you can see a lot of action. You have to get really close to the action to see all this dynamic stuff. And something you see here is, for example, when you're really close to the black hole, there is a lot of dust and gas going in, but then the black hole starts eating, it gets hungry, and then it starts expelling stuff, and then it clears up. So there you have your quasar. And that quasar is supposed to launch all these winds that are going to create these galaxies. That's what we thought. Let's see if that happens. So we looked at this example. Here's the gas, which is the fuel for star formation. And when those circles turn into stars, it means that you're making stars. This is in the simulation. So this thing went quasar, and then you start making stars. So hey, you're actually making like a little object inside the galaxy because of the quasar. And this is, we wrote this paper, this is really nice. Unfortunately, this is inside the galaxy. We're able to create like mini galaxies, but these are inside the galaxy, not outside. These are more like the globular clusters I told you about. So with the physics we know, in our simulations we're not able to create galaxies without dark matter with quasars. We kind of ruled that out. And Priya was really mad at me, but I'm okay with that. Anyway, she's a good friend. So the second idea, well, maybe it's, we saw that massive galaxy and the neighbors, maybe interactions between them is the way to go. So we said like, well, this is the paper I wrote after I knew the answer. What I did is I was like, you know what, I'm not gonna be biased. I'm just gonna look for galaxies without dark matter. And then I'm gonna look at the physical mechanisms that explain it, and I'll see what happens. And this turned out to be the answer. So I invite you to read this paper, and if you can't fall asleep, you can read it and it will send you to bed. So we ran this massive simulation. I show you a simulation with dark matter only before. This one has the stars and the gas and the black holes, everything in it. And in my opinion, this is the best simulation so far. I'm biased because I made it. But in the simulation, we find that it's very consistent with all the observations you have about galaxies. It matches all the data really well. It requires the presence of dark matter. You have to have dark matter halos in most of the galaxies. But we found 7 that have very little dark matter. And I gave them these names. It's wolf, wild potato, pain, blue, long-haired bird, and deer. Now I live in Southern California. I have friends who live in Orange County. So I'm like, well, what should we name these 7 galaxies? And they're like, oh, what about like the 7 dwarfs? And I was like, I mean, I thought it was cute, but it was like, I have friends with dwarfism, and I didn't think it was cool to denigrate them with my paper. Like, so I've been humbly inviting the community to maybe we can move away from calling them dwarf galaxies. We can call them tiny, we can call them puny, we can call them low mass. So I'm not going to call them that. Someone else said, well, what about the 7 sisters of Greek mythology? And I told myself, I'm not Greek, I'm not a woman, maybe it's not really my place. I'm a person of indigenous ancestry. My ancestry is mostly Huichol. There is some Kickapoo in there, some Apache in there. That's what I heard from family. And Huichol is a really strong presence in me because of my mother. Well, what about indigenous cultures? Is there anything there? I have a friend who lives in Dallas-Fort Worth. He's Cherokee. And he told me about the Cherokee tribe. They have 7 clans. And each clan has its own personality, its own cuisine, its own culture. And the heritage is passed through the mother, so it's a matriarchy. As it should. I think it makes more sense for the lineage to go to the mother because they're the ones who give birth, right? So that's what they do. So I told him, look, can you talk to the elders, to the leaders of your tribe, and so I can to ask them permission for me to use these names, and they say yes. So that's what I named them, and each of the clans has a personality. You're gonna see that each of the galaxies has a personality. Let me introduce them to you, and just keep in mind there's gonna be a quiz. Okay. So here's the first one. This is Wolf. This is a simulated galaxy. This galaxy lives in a computer. But I created it so that it looks like a real galaxy. And if this galaxy were real, you would be able to see it with the Hubble Space Telescope. So it's to a massive galaxy. And it's kind of cute. But in the simulation, we know we can actually visualize where the dark matter is. So this is where the dark matter is. A massive galaxy has a really massive dark matter halo. This little satellite doesn't. Has no, what we call a subhalo. This one is wild potato. And again, it doesn't have dark matter. Paint is kind of fluffy like me. And this one also doesn't have dark matter. So here's the quiz. What do these 3 galaxies have in common? So I'll let you talk to each other for 2 minutes. And if you're extremely shy, your opportunity to shine and challenge yourself and speak up. If it's really hard, you can ask the person next to you, hey, can you share this idea with the room? But otherwise, give it a shot. I think this is a friendly community, so let's give ourselves a couple of minutes and let's see what we come up with. We're gonna put on our scientist hat and try to answer that question. What do these 3 galaxies, the ones in the white circles, the little ones, have in common with each other? Go. I'll put you in the spot. All right. Do you need more time? If you can hear me clap once, if you can hear me clap twice, you can hear me clap 3 times. All right. So what do they have in common? They are next to a bigger galaxy, yes. They have clusters of gas.
I think they covered what I...
They cover, yeah, gray minds think alike.
They're regular shape.
They're irregular shaped, like they have these tails, right? Like, yes.
They are all oriented in a rectangular fashion, so that means then that none of the stars around the perimeter are going around the center of these guys.
Yeah, so like these tails are kind of tracing the trajectory, just like a comet going around the sun. The tail tells you more or less the trajectory of the comet. I see. So maybe there is a connection between how massive the big one is and how far away it is. And you said that's true also that they are kind of next to the massive galaxy, right? Anything else? I see some people wearing kind of like yellow, other people are wearing blue. I don't know. I like a lot of color in my life. Anything about color? So these ones are kind of bluish. They have a lot of blue light. These ones are more like yellowish, right? That actually means that they don't have any new stars. They're out of fuel. They're not making any stars anymore. Anything else? There is one last thing that they have in common. It's an obvious thing. No dark matter. Yes. No dark matter. Yes. Thank you. Thank you. All right. So I told you there were 7. These are 3. The next one is long hair. This one is kind of far away. This one is weird. It's coming in an extremely radial orbit. It crashed into the massive galaxy. It went to the other side. It left. It stopped being a satellite. It left the halo, and now it's on its way back. And this is its dark matter halo, like a boomerang. Yeah. And the last 3, they're all together. They're friends. They're a family. Deer is also fluffy like me. It's a really fun one. And Blue and Bird, they came together just like the clouds around the Milky Way. They've been dancing a long time, just like my wife and I. And we came in here into this beautiful, majestic space. Blue and Bird are like that. They are married, they are been dancing together, and now they're members of this group. And they don't have dark matter. So how the heck do you make them? There are 2 conditions. And I think you helped me get through the answer by thinking as scientists. Everybody is a scientist. Everybody can do science. We saw that there's a clue about these 2 interacting with each other, and you see the tails. So we find in the simulation that in order to become a dark matter efficient galaxy, you have to interact with a more massive galaxy that's around 1,000 times more massive. So the ratio between these 2 has to be around 1 to 1,000. It cannot be 1 to 100. It cannot be 1 to 100,000. What we find, if it's the mass ratio, if they are 2 similar to each other, they just merge. They just assimilate one with the other. If the mass ratio is really discrepant, like 1 to 100,000, the little guy gets completely destroyed, like the video I showed you before. But there is a sweet spot where they don't get destroyed. It's kind of weird, like you come into this space and you're given 2 options. Either you assimilate, or you are disrupted. And these are the troublemakers. They're like, no, we're not going to go away. We're going to confront you multiple times. But they pay a price. They lose dark matter. So that's the first condition. The second one is they have to be in orbit so that they come within 5% of the dark matter halo of the host. So you have the massive galaxy. You have its dark matter halo. You take the radius. Take 5% of that. These galaxies go within that region multiple times. So I call those extreme encounters. So to produce galaxies lacking dark matter, you need these extreme galactic encounters. And this really brings me back to the naming of these galaxies. And because these are indigenous cultures that they survive a lot. President Jackson deported them. Some people went into hiding. Some people went into a civil war within the tribe. Some people assimilated. They changed their names, right? If you listen to me, I'm a person of indigenous ancestry, but I have a European name. I only speak European languages. I wear European clothes. I was assigned a European gender. But I'm still here, even though my people lost their culture or their cuisine or their dark matter, we're still here. And let me expand that not just to indigenous people, but to everybody. All of us, if you go back 10,000 years, our ancestors were all together in South Africa. It was the Ice Ages, and there were only a couple of thousand people. They were surviving by eating clams or potatoes. But they were clever, they were insightful, they were imaginative, and they supported each other. And thanks to them, all of us are here today. So as you leave this room, I want you to think about the challenges that the world is facing. Climate change, war, inflation, we have an election. And rather than thinking about how different we are, I want you to reflect about how similar we are. And that our ancestors have proven that we can get here. Think about what kind of descendant you want to be, or what kind of ancestor you want to be to the people that are coming after you. Thank you for your generous attention. It's been a pleasure to be here. So light goes through it because dark matter particles don't interact with light.
They just don't.
They just don't listen to it.
Did you find parallels in real galaxies like this?
Yeah, so the first two galaxies, the F2 and the F4, those are real galaxies that exist in the real universe. And the challenge was, can we use physics to explain them? So we found these 7.
So what you have found through your simulations here are matched by what you see.
Yes, and we're the only group in the world who's able to reproduce galaxies like the ones in the observations.
Does the black matter have an energy signature?
Does the dark matter have an energy signature? So there are some models in particle physics that say like the dark matter are weakly interacting particles that they can decay and then emit some sort of light. So they go from dark matter, they emit into something that can emit light. So, and it could be X-rays or gamma rays. So some people are looking at the center of the galaxy for gamma rays because that could be a remnant of dark matter that decayed into luminous matter. But it's, who knows?
This is a silly question, but these smaller galaxies are moving in a relationship to the larger galaxy. Does that have any effect?
Yeah, so, and this has a really strong effect. So the fact that, so you have this massive galaxy, and this one, because there is a stronger gravitational field, this one is going to fly into it very quickly. And what happens is when it crosses the big galaxy, it loses its dark matter. So the bigger galaxy is kind of like taking away the dark matter.
This is perhaps off topic, but in your simulations, I see that the galaxies have quite a bit of angular momentum, and I'm wondering where that comes from.
So let's see. So angular momentum is a natural thing that happens in the universe. So if you have a non-homogeneous distribution of matter, if you have a little more matter here than here, that's going to turn me into spinning.
Angular momentum has to be conserved,
Total angular momentum of the universe is conserved.
so the total angular momentum of the universe is 0. Otherwise, where would it have come from?
Well, why would it be 0?
Well,
Well, it would be conserved. It's,
wondering
it's,
where angular momentum came from if the universe has angular.
so angular momentum came from the homogeneous distribution of matter in the initial universe. Yes. I saw a question here. Yes.
How many solar masses are the stars in the Milky Way versus the entire Milky Way?
So the Milky Way, if you look at the stars themselves, is like 50 times more massive. Yeah. Ooh, dark energy. If we know very little about dark matter, we know next to nothing about dark energy. So what dark energy is doing is driving the expansion of the universe. It's hypothetical, but it's the best explanation we have to explain the accelerated expansion of the universe. Yes. Yes.
Is anybody like trying to figure out how to use artificial intelligence and like I don't know. You said you do a lot of work with supercomputers. That's why I thought maybe.
To write a grant so that we can teach a computer to identify features in galaxies that tell you information about their dynamic, how they orbit. Then we can say it's likely to have had this. We cannot take galaxies today and run them back in time, but we can look for those imprints. We can look for them visually, or we can let a machine find them. I'm not an expert on machine learning. I had a postdoc who is, so I'm planning to spend some time doing it. Yeah, machine learning and AI, it's a really nice tool. We need to be careful with it, but it can do good things.
Last question.
Oh, I have another one, and it's about, like, Milky Way now has 2 baby galaxies, right? The large and small, what are they, Magdalene?
Some people call him the Magellanic Cloud, but Magellan was an awful human being, so I just call him the cloud.
The clouds. How do they relate to this? I mean, what is their dark matter relationship to the Milky Way, or is there any?
So what the simulations show is that these galaxies have been interacting with each other, so they kind of incite each other into making stars. If you're a galaxy and I'm a galaxy and we're dancing, we're going to help each other have new stars born. But also the bigger galaxies kind of taking away our stars and our dark matter.
So they are
Yeah.
So the Milky Way is sucking things
Yes.
out of those clouds.
Yeah, and one of the questions I have is, are they going to merge with each other or are they going to merge with the Milky Way? We don't know yet. Yeah. It's a lot, it's very interesting, right? It's a lot of fun. All right.
So we'll be able to take a few more questions afterwards, but join me in thanking Dr. Moreno.
Thank you for your generous attention.